I think we can go. You have about 45 minutes plus 5 of questions. So it is a pleasure to have here today Dimitrios Bachtis from Swansea University and ITN Europlex, who will tell us about machine learning and inverse renormalization group. Dimitrios, anytime you're ready.
Yeah, so thank you very much for the invitation. I wish I was there, but nevertheless, I really enjoyed the previous days. So I will be talking about machine learning in relation to phase transitions as well as the inverse renormalization group. So there are two different research directions that I will discuss, and the first one is the interpretation of machine learning functions as physical observables. So on that part, I want to answer the questions how to construct effective order parameters with machine learning, how to reweight machine learning functions in a system's parameter space, how to discover unknown phase transitions by using machine learning, also how to include machine learning functions within Hamiltonians to induce phase transitions in systems, and how to utilize the renormalization group to obtain critical exponents using machine learning functions. The second research direction that I'm going to discuss is about the inverse renormalization group when it is combined with machine learning. So I want to answer the questions how to generate configurations of systems with larger lattice size without having to simulate these systems and therefore without experiencing critical slowing down effect, how inverse renormalization group flows emerge in a system's parameter space, and how to calculate multiple critical exponents based on arguments established with the inverse renormalization group. So I will start by describing supervised machine learning for phase identification. So this topic has been explored a lot in the past 5 or 6 years. So there is a vast number of publications that show how to make supervised machine learning for phase identification work. And in a supervised framework, we can train a machine learning algorithm on a set of training data to learn a function f that separates the symmetric and the broken symmetry phases of a system. So we require a set of configurations from distinct phases, and each configuration has been labeled accordingly to the phase that it belongs to. And of course, we also need a machine learning algorithm. I explicitly state this because different algorithms have different benefits or different limitations. So to make this clear in terms of a figure in the case of the Ising model, so we have a set of configurations that we have labeled as 0 or 1, depending on the phase that they are in. And we give them as input to the neural network. They get processed through a series of transformations, and at the output we have the label that corresponds to the phase of each configuration. And through forward and backward propagation, the neural network eventually learns the best function f that is able to accurately separate these configurations. And after the neural network is trained, we can actually use it to predict the phase of an unknown configuration. So this is a configuration that the neural network has never seen before. We give it as input, it gets processed through these transformations, and at the output, we have a result. So we interpret this result as the probability that this configuration belongs in the broken symmetry phase. So at this point, we can actually make the first important observation. So this configuration has been drawn from an equilibrium distribution, so it has an associated Boltzmann weight. The output is a physically meaningful quantity. It expresses the probability that this configuration belongs in the broken symmetry phase, and this quantity has been calculated on this configuration based on a series of transformations. So we expect that the output should have the same Boltzmann weight as this configuration. So in other words, what I'm saying is that by definition, the neural network function is an observable in the system. And its expectation value can be written as a sum over all states weighed by the associated Boltzmann probability distribution. So what this means practically is that this neural network function has the proper dependence on the inverse temperature of the system. And we can therefore use histogram reweighting to extrapolate it in the system's parameter space. So I will briefly describe histogram reweighting. So this is the expectation value or the numerical estimator of an arbitrary observable as obtained during a Monte Carlo simulation. P tilde are the probabilities that we use to sample from the equilibrium distribution. So if we select these probabilities equal to the probabilities of the inverse temperature that we want to sample, then we do importance sampling. This is the common way that we do Monte Carlo. However, if we select the probabilities of a sufficiently adjacent inverse temperature in parameter space, then we have some form of histogram reweighting. So if we select these probabilities, then we arrive at this reweighting equation. And what this equation says is that given configurations are sampled at a specific inverse temperature beta 0, we can calculate the expectation value of observables at another inverse temperature beta. Of course, we discussed that the neural network function is unobservable. So as a result, we can use the reweighting equation. So here is the result. This is the neural network function versus the inverse temperature. And this field point corresponds to the Monte Carlo dataset that we used to conduct reweighting. You can see the extrapolation of the neural network function with this red line. And of course, we had to compare this with independent calculations that you can see with these empty points. You can see that the results agree within statistical errors within the insets, therefore certifying that reweighting of neural network functions in a system's parameter space is possible. So a second important observation based on this figure is that the neural network function looks like an effective order parameter. It has the value of 0 at one phase and the value of 1 in the other phase. So we then thought that we can use this neural network function as well as its fluctuations or the susceptibility to conduct a finite size scaling analysis and see if we can obtain the critical exponents of the system. So here is the finite size scaling analysis, and the results are summarized in this table. You can see that by using the neural network as well as reweighting, we are able to calculate accurately the critical inverse temperature as well as the correlation length exponent and the magnetic susceptibility exponent. And the results agree within statistical errors with Onsager's analytical solution of the two-dimensional Ising model. So in summary, I have answered these questions now: how to construct effective order parameters with machine learning and how to reweight machine learning functions in parameter space. So in summary, no knowledge about the symmetries or the Hamiltonian was explicitly introduced during the training of the machine learning algorithm. The reason is that we trained the machine learning algorithm on a set of configurations. We never introduced any information about the Hamiltonian that produced these configurations during the construction of the neural network function. We also saw that neural network functions are statistical mechanical observables. They are associated to a Boltzmann weight, and we can therefore reweight them in the system's parameter space. And we also saw that by using only the neural network function and its susceptibility, we were able to obtain multiple critical exponents as well as the critical inverse temperature for the two-dimensional Ising model. So now I want to move to the next set of questions. And we saw that the neural network function is for all practical reasons unobservable in the system. But what else can we achieve with this neural network function? So we saw that this function was learned on configurations of the Ising model, and it was able to successfully predict the phase of Ising configurations. But what happens if we give configurations of a different system as input to this Ising length function? Can we accurately separate phases in different systems? And can we discover a phase transition if we don't know that a phase transition exists in a certain system? So to make this more clear, let's say we have configurations from the Potts models. So the Potts models have dramatically different physics when the number of states is greater or equal to 3. Also, the systems are described by discrete degrees of freedom that are non-binary. Also, let's consider that we have configurations from the phi to the 4 theory. The phi to the 4 theory has a second order phase transition, which is conjectured to be in the Ising universality class, but at the same time, the system is described by continuous degrees of freedom, not binary. So if we give these configurations as input to this Ising trained neural network, will we get the proper result? In other words, will this Ising trained neural network be able to accurately separate the phases for these systems? So here is the result for the Potts models. You can see that the Ising-trained neural network is able to predict a phase diagram, a phase transition for all of these cases, even when the universality class of the phase transition changes, and even when the order of the phase transition changes. Also, these results are compared with where we expect to find analytically the phase transition, which is depicted by these dashed lines for all of these cases. Also, here are the results for the phi to the 4 scalar field theory. To the best of my knowledge, there exists no analytical solution for the model that shows where the phase transition is located. So we compared it with the literature, and we found that the neural network gives the correct result for the critical region. So now we would like to get some further insights into these results, into why this method works. So one idea is to slice the neural network at a certain point and see if we have some consistent results at that specific layer. In other words, what we want to do is we want to find if the neural network has learned some form of universal features that are able to differentiate between the symmetric and the broken symmetry phase for all of these systems. And here are the results. So these are the variables at that specific layer. And at the top, you can see that there is a certain set of variables that get triggered when we give configurations from the disordered phase, irrespective of the system, and another set of variables that get triggered when we give configurations from the ordered phase, irrespective of the system. So this indicates that the neural network has learned some form of universal features that are able to differentiate between the two phases. So now I wanted to emphasize that we didn't include any knowledge about the presence of a phase transition in all of these systems. So we have now obtained the knowledge of the critical region, which means that we can follow exactly the same procedure as the one that I showed you for the Ising model at the beginning to calculate the critical squared mass as well as the critical exponents for the phi to the 4 theory. So here are the results, and you can see that we were able to obtain the critical squared mass as well as the correlation length exponent and the magnetic susceptibility exponent, and the system is also conjectured to be in the Ising universality class. So now I have answered this question, how to discover unknown phase transitions with machine learning. So using an Ising-trained neural network, we were able to predict the phase diagram for the Q-state Potts models as well as for the phi to the 4 scalar field theory. And having obtained the knowledge of the critical region for the phi to the 4 theory, we were then able to calculate the critical exponents and the critical squared mass for the system. So now to move on, how can we explain that the neural network function is a statistical mechanical observable? Of course, the neural network function is a quantity that we can calculate on a configuration, but how can we explain this further? So we know from statistical physics that parameters, constraints, or fields that interact with a system have conjugate variables which represent the response of the system to the perturbation of the corresponding parameter. Examples are the pressure and the volume. Another example is the magnetic external field and the magnetization. So can we make the same statement about the neural network function? In other words, can we view the neural network function as a conjugate variable that has its own associated field? So to be able to do this, we should start by expressing the neural network function in terms of the free energy or of the partition function of the system. The reason is that conjugate variables are always expressed as derivatives of the free energy in terms of their associated field. So at this point, I should emphasize that the words field, constraint, or parameter are exactly equivalent. So this neural network function is an intensive property. It is interpreted as a probability, and it is therefore bound between 0 and 1. As a result, it doesn't have the proper dependence on the size of the system, and we can only introduce extensive properties within Hamiltonians or axioms. So this is something that we can very easily solve by multiplying the neural network function with the volume of the system, and therefore recast it as an extensive property. So now we can include this neural network function as a term within the Hamiltonian. Specifically, we consider that the neural network function couples to an arbitrary fictitious external field, and we define this modified Hamiltonian for the Ising model. If this neural network field is equal to 0, then we have the original Hamiltonian of the system, and we therefore haven't changed anything. So if we take a first derivative of the logarithm of the partition function in terms of this fictitious neural network field, we arrive at the expectation value of the neural network function. Again, if this neural network field is equal to 0, then we have the original expression and we didn't really change anything. If we take a second derivative in terms of this neural network field, then we arrive at this expression that we recognize as a susceptibility. And this susceptibility measures the response of the neural network function f to changes in the associated neural network field y. So at this point, someone can very well ask what happens if this neural network field is not equal to 0. So mathematically, this is like asking the question, what happens if we allow a statistical system to interact with a neural network that has been trained to accurately separate its phases? And this neural network field measures the strength of the interaction. So to investigate what happens when this neural network field is not equal to 0, we could do Monte Carlo sampling on this modified Hamiltonian to obtain configurations. However, we want to avoid this because we can use reweighting to calculate expectation values for this modified system by relying on configurations of the original. So I will briefly describe this form of reweighting. So now we consider the expectation value of an arbitrary observable as obtained during a Monte Carlo simulation in the modified system that we aim to sample. And this time we will select the sampling probabilities equal to the probabilities of the original system. So we obtained this form of reweighting. So the important observation is that this form of reweighting is Hamiltonian agnostic. So what I mean by this is that, as you can see in this expression, the Hamiltonian or the axion of the system does not appear. So to use this form of reweighting, one only needs a certain set of configurations and a neural network to train these configurations on. They don't need to know what is the form of the axion or the Hamiltonian that produced these configurations. So here is the first result. This is the neural network function versus the neural network field for 3 cases of temperature in the Ising model, 1 below the critical point, 1 at the critical point, and 1 above the critical point. You can see that irrespective of the phase that we start in, by varying this neural network field, we are able to induce an order-disorder phase transition in the Ising model by breaking or restoring its symmetry. So remember that this is the probability that a configuration belongs in the broken symmetry phase. So when it is 1, we are in the broken symmetry phase, and when it is 0, we are in the symmetric phase. So now that we have this first indication that we have a phase transition, we can also calculate the susceptibility of the neural network function versus the neural network field. And you can see that for all of these 3 cases, we have a maximum value in the susceptibility, therefore indicating the crossing of a phase transition. So now that we saw that the neural network field is able to induce a phase transition in the system, can we study this phase transition with the renormalization group? So here is a configuration of the 2-dimensional Ising model for a moderately large lattice size. You can see all of the fine details in this system. For example, some of the spins that point in different directions. And you can also see that this configuration has been drawn close to the phase transition because it has a certain correlation length. We can see this because we have some clusters that have a certain size. So now we want to apply our renormalization group transformation with the majority rule on this configuration. So what we will do is we will separate the lattice into blocks of size 2 by 2, and we will select the rescaled degree of freedom based on the majority of the spins within each block. When the number of spins is equal, we make this choice randomly. So I want to emphasize that for today's talk, I will always consider that the rescaling factor is equal to 2. So if we start from a system that has a certain lattice size L in its dimension, then by applying a standard renormalization group transformation, we are going to halve the lattice size in its dimension. So here is the application of this renormalization group transformation on the original configuration. You can see that some of the fine details have disappeared, but nevertheless, these two configurations look very similar to the human eye, and the reason is that the rescaled system preserves the information that exists in the original. So as I mentioned, the application of a standard renormalization group transformation reduces the lattice size by a factor of 2 in each dimension. But as I mentioned before, the original system has a certain correlation length psi. So by reducing the lattice size by a factor of 2 in each dimension, we are also reducing the correlation length by the same factor. However, we all know, because this is a workshop about phase transitions, that the correlation length is a quantity that increases as we approach the critical point. So because these two systems have different correlation lengths, they have a different distance from the critical point. And what this means practically is that these two systems are also described by different inverse temperatures, beta and beta prime. So now I will give you exactly the same intuition using a figure instead. So this is a figure of the correlation length versus the inverse temperature for the case of the Ising model. So let's assume that we started below the critical point, specifically at this specific inverse temperature where we have a certain correlation length. By applying a standard renormalization group transformation, we are going to reduce the correlation length, and as a result, we will drive the system towards the 0 inverse temperature. If we are above the critical point, then by reducing the correlation length, again, we are going to drive the system towards the infinite inverse temperature. However, there exists a certain inverse temperature where the correlation length is equal for the two systems, and that's the inverse critical temperature. At the inverse critical temperature, the correlation length diverges, it becomes infinite or 0, and intensive observable quantities of the two systems will become equal. So in a large part of the talk, I emphasized that the neural network function is unobservable in the system, so why not use it to locate the critical point? So here you can see the result. This is the neural network function versus the inverse temperature for an original and a rescaled system of the same lattice size. You can see that the two neural network functions intersect at a point in parameter space, which is our first estimate of the critical fixed point. Now we would like to generalize this idea, what you see in this figure. So to give you the intuition, let's select a certain value of the neural network function, for example, 0.6, and you can see that the original system has this value at a certain inverse temperature and the rescaled system at a different inverse temperature. So now we want to obtain an expression that allows us to relate the original and the rescaled inverse temperatures based exactly on the data depicted in this figure. So that's something that we can do with the mapping that you see at the bottom. So here are the results that we obtain for the original and the rescaled inverse temperatures, and now we can actually do our first quantitative calculation of the critical fixed point, and we obtain this result. So you see that this result is extremely accurate, even though it has been calculated on a trivially small lattice size, specifically L equals 32 in each dimension for a two-dimensional system. The reason is that the renormalization group is a technique that does not suffer from as strong finite size effects as finite size scaling. So we are able to obtain quantities related to criticality at much smaller lattice sizes. So now you remember that the original and the rescaled systems have a different distance from the critical point, and this distance can be explicitly measured by defining the reduced inverse temperature for the original and the rescaled system. I also mentioned that the two systems have different correlation lengths, which means that they should diverge to the thermodynamic limit according to different relations. However, the correlation length exponent is identical for both systems because both the original and the rescaled systems are Ising models. So if we now divide these two expressions and we linearize the renormalization group transformation in the vicinity of the phase transition with a Taylor expansion to leading order, we are able to obtain this expression that allows us to numerically calculate the correlation length exponent. So we will now do this on the data that I showed you before on this figure. So we do the calculation in the vicinity of what we have estimated as the critical fixed point. And we are now able to calculate the correlation length exponent, where again, you see that the calculation is extremely accurate, even though it has been obtained on a very small lattice size. So now we also show that the neural network field is able to induce a phase transition in the system. Of course, because the neural network field can induce a phase transition in the system, this instantly implies that the neural network field affects the correlation length. So we can define a novel critical exponent that governs the divergence of the correlation length in terms of this neural network field exactly at the critical point. So following exactly the same procedure as the one that I described for the Ising model, we can construct a mapping that relates the original and the rescaled neural network fields. And we can obtain this expression that allows us to numerically calculate the neural network field exponent in the vicinity of the phase transition. So this time we do the calculation as the neural network field goes to 0, and we are able to obtain this critical exponent. So we know that the Ising model has two relevant operators that govern the divergence of the correlation length. These are the exponents nu and theta. And these are the exact values of these two exponents. So the exponent theta governs the divergence of the correlation length in terms of the magnetic external field, and this is its value. So we see that the neural network field exponent overlaps within statistical errors with the exponent of the magnetic external field. So we presume that these two exponents are identical, or in other words, that the neural network field exponent is one of the two relevant operators of the Ising model. So now I have answered these questions: how to include machine learning functions within Hamiltonians to induce phase transitions in systems, and how to utilize the renormalization group to obtain critical exponents using machine learning functions. So in summary, we introduced neural network functions as physical terms within Hamiltonians by coupling them to a fictitious field and expressing them in terms of the system's partition function or the system's free energy. And we also observed that the neural network field Y is able to induce an ordered disorder phase transition, which is in contrast to the field of the conventional order parameter, which always breaks the symmetry explicitly by favoring an ordered state in the system. That is irrespective of the sign that it has. And we also utilized the renormalization group to extract the two relevant operators of the two-dimensional Ising model using the neural network function and its fictitious field Y. So now I want to move to the final topic of this talk. So can we devise an inverse renormalization group approach that can be applied for an arbitrary number of steps to iteratively increase the lattice size of the system? If yes, then this means that we can obtain configurations of systems with larger lattice size without having to simulate these systems, and therefore without experiencing the critical slowing down effect. So in contrast to the standard renormalization group in which we eliminate degrees of freedom within a system, in the inverse renormalization group, we are going to introduce degrees of freedom within a system. And of course, this is something that complicates things. So I want to first give you the intuition in the case of the Ising model. So let's assume that someone wants to invert the majority rule in the Ising model, and they have this original degree of freedom. Then all of these degrees of freedom that you see right here are possible solutions, because if you apply the majority rule in all of these cases, you are going to get your original degree of freedom. So even though there is not a unique solution, at the same time, all of this is a countable set. You can literally write down all of the possible rescaled degrees of freedom. And at the same time, I want to emphasize that the inverse renormalization group has already been applied in the case of the Ising model, and here is the paper if you want to check it. Now, even though this looks complicated, at the same time, it's simple compared to the case where we have a system with continuous degrees of freedom, such as the phi to the 4 theory or any other system. So if we consider that we have this original degree of freedom and we want to invert a simple summation, then we literally have an infinite number of possible rescaled degrees of freedom. And the problem is that all of these rescaled degrees of freedom can look dramatically different between them, which means that if we apply this transformation a second time, then we are going to have major problems. Practically, we are not going to get a system that will look like a phi to the 4 theory at all. So the problem is very complicated. At the same time, this is exactly the point where one hopes that with the use of machine learning, they can simplify this problem and they can obtain the solution. So we thought that we can learn a set of transformations that are able to mimic the inversion of a standard renormalization group transformation. So to make this explicitly clear, we start from a system of a certain lattice size, and we apply a standard renormalization group transformation on the phi to the 4 theory. We then obtain a set of configurations that are rescaled, that have half the lattice size. And we then treat their inversion as a machine learning problem. So we learn a set of transformations in the form of transposed convolutions that once applied on the rescaled system, they can produce a model system that has the same lattice size as the original. We then minimize the mean squared error function between the original system and the one that we obtained from this machine learning algorithm until we learn the best set of transformations that are able to reproduce the original lattice size from a rescaled one. So I will briefly give you the intuition of what it means to apply a transposed convolution. So if we have a certain lattice and we want to apply this transposed convolution in the system, we have a set of weights, W's. So if you consider that these have a certain value, then the application of a transposed convolution is going to produce a system of larger lattice size. At this point, I wanted to emphasize that you don't have to apply only one set of transposed convolutions. You can apply 100, for example. At the same time, you don't only have to apply them once, you can apply them more than once and also manipulate the lattice size that you got at the bottom. Then you can also apply another set of convolutions to reduce your lattice size. So you can control the lattice however you like. And the benefit of the method is that once learned, this set of inverse transformations can be applied iteratively to arbitrarily increase the size of the system. Of course, this happens with a certain rescaling factor, and as I mentioned before, we always consider in this talk that the rescaling factor is equal to 2. So every time that we apply this set of inverse transformations, we double the lattice size in its dimension. However, the increase in the lattice size will also induce an analogous increase in the correlation length of the system. So what are the implications of this increase in the correlation length? So before, in the standard renormalization group, I showed you that by applying a renormalization group transformation, we reduce the correlation length and we therefore drive the system far from the critical point. Now in the inverse renormalization group, because we increase the correlation length, we drive the system closer to its critical fixed point. So to make this explicit of how the method works, first we verify that the standard Monte Carlo renormalization group method works in the phi to the 4 theory. So here you can see the magnetization versus the squared mass for the case of the phi to the 4 theory, where we have applied the conventional renormalization group approach. And you can see that the proper behavior has emerged. Specifically, we have a critical fixed point and the system is driven far from the critical point. So we have the proper renormalization group flows. So now that we have verified that the standard renormalization group method works in the system, we can invert this successful renormalization group transformation using exactly the procedure that I described before. with the transposed convolutions. So what we do now is we start from a lattice size of L equals 32 in its dimension and apply the inverse transformations to obtain systems of lattice size 64, 128, 256, and 512. So we never have to simulate these systems, we only have to simulate the original lattice size. So here is the first result. You can see the rescaled systems, the magnetization for the rescaled systems with these dashed lines, and the width indicates the statistical uncertainty. And specifically for this case, we also simulated the original systems to allow for a direct comparison. You can see that the proper inverse renormalization group flows have emerged in a system's parameter space. So below the critical fixed point, the rescaled magnetization has smaller value than the original because the system has been driven towards the critical fixed point. The same holds above the critical fixed point. Specifically, the rescaled value of the magnetization is larger because the rescaled system has been driven again towards the critical fixed point. So now I want to emphasize that one does not have to simulate the original systems in all of these figures. The only reason that we did it was because we wanted to establish the validity of the inverse renormalization group. In fact, someone does not want to simulate the original systems because if we simulated the original systems for all of these lattice sizes, we will still have critical slowing down effect. So we can still calculate whatever quantity we want without simulating the original system. So the expressions that give the divergence of the magnetization for an original and a rescaled system are given right here, and this can be equivalently expressed in terms of the correlation length. Again, I want to emphasize that the magnetization exponent is identical for the original and the rescaled systems because they are all 5 to the 4 theories. So by dividing the magnetizations or the magnetic susceptibilities, taking the natural logarithm and linearizing the renormalization group transformation with L'Hopital rule, we are able to obtain these expressions that allows us to numerically calculate the magnetization exponent and the magnetic susceptibility exponent in the vicinity of the phase transition without ever experiencing the critical slowing down effect. So here are the results. In the table at the top, you can see the results when we started with a system of lattice size 32 in its dimension, and we applied the inverse transformations until we obtained a system of lattice size 512. And we then used the inverse renormalization group to calculate these two critical exponents for all of the combinations of these systems. You can see that as the lattice size increases, we can observe a convergence towards the critical exponents of the Ising universality class. So again, I mentioned that there is a conjecture that the 5 to the 4 phase transition belongs in the Ising universality class. So then we wanted to see how well this works when we decrease the lattice size. So we started from a system of lattice size 8 in its dimension, and we applied these inverse transformations until we obtained again a system of lattice size 512. Again, you can see that as the lattice size increases, as we do the comparison on larger lattice sizes, we can again observe a convergence towards the exponents of the Ising universality class. So I want to emphasize that to obtain these results, we only had to do one simulation. This is the simulation for a lattice size 32 at the table at the top, and for a lattice size of 8 in its dimension for the table in the bottom. So now we have answered these questions, how to generate configurations of systems with larger lattice size without having to simulate these systems and without experiencing the critical slowing down effect, how inverse renormalization group flows emerge in a system's parameter space, and how to calculate multiple critical exponents with the inverse renormalization group. We demonstrated that inverse renormalization group transformations can iteratively increase the lattice size of a system. As a result, we are able to obtain configurations of larger lattice size without critical slowing down. We also demonstrated that the inverse renormalization group flows that emerge in the system's parameter space drive the system closer to its critical point. And we also demonstrated that multiple critical exponents can be calculated for the phi to the 4 theory based on arguments established in the inverse renormalization group method. So to conclude, I discussed two different research directions. The first one was the interpretation of machine learning functions as physical observables. And the questions that I got answered was how to construct effective order parameters with machine learning, how to reweight machine learning functions in a system's parameter space, how to discover unknown phase transitions with the use of machine learning, how to include machine learning functions within Hamiltonians to induce phase transitions in systems, and how to utilize the renormalization group to obtain critical exponents based on machine learning functions. And the second research direction that I discussed has to do with the inverse renormalization group. So I discussed how to generate configurations of systems with larger lattice size without having to simulate the systems and therefore without critical slowing down effect, how inverse renormalization group flows emerge in a system's parameter space, and how to calculate multiple critical exponents with the inverse renormalization group. So that should be all. Thank you very much for your attention. And if you have any questions, I will be very happy to answer them.
Thank you, Dimitrios. Let's thank Dimitrios. Questions from the audience here, the live audience. Yeah, perhaps we can go with Wei Yen's.
Yeah, thank you very much for this very interesting talk. Sorry to be so critical, but you make so many claims that provoke this. So it sounds a little bit too good to be true, but I have not studied this at all. I mean, if I understand correctly, especially the second part of your talk, I didn't hear the very beginning. You are using a 32 by 32 lattice, and then you do your inverse renormalization group, which means to train the system, you probably do the 64 by 64 as well. And then based on that type of input, you go all the way to 512 squared. But there is only so much information in the smaller systems. And it is, for me, difficult to imagine how you actually get the details, the fine details of the bigger 512 from those systems. So if you would do very precise calculations, I imagine that your 512 doesn't really know more than the smaller systems. So where does the information come from, since it was not there in the beginning?
Yeah, so the information is actually entirely related to the dependence of the correlation length that you have forced the machine learning algorithms to learn. So to correct a little bit, we don't start from 64, we start from 32 and we reduce the lattice size to go to 16. Then we learn with the machine learning algorithm how to go back to 32. Mm-hmm. So the only reason that this works is because through this machine learning approach, you always have learned how to double your correlation length. So because you have certified that, you can go in principle as large lattice sizes as you want. So another question that will be more valid is how can you certify that in a way you haven't introduced an inaccuracy, so that, for example, this might not be exactly double your correlation length. But as long as you have learned a set of inverse transformations that can double your correlation length, in principle, you can go as large as you want. Actually, in the case of the Ising model, they start from much smaller lattice sizes. I think they start from 4 in its dimension, and they are able to go up to 1,000, I think. Mm-hmm. But of course, that's much more simple in the case of a binary system, I think. I think it's easy to understand with physical intuition that it's much more simple to do that on a discrete spin system.
Mm-hmm. Maybe I can challenge you a little bit.
Yeah, please.
So, long time ago, we worked on the three-state Potts model, but in 3 dimensions, where it has a rather weak first-order phase transition, is sort of a mimicking the Yang-Mills theory of finite temperature transition. And then we introduced the chemical potential. I think Fridtjof Karsh did a similar calculation with a student at that time. And then you weaken the phase transition, and ultimately it ends in a second-order critical endpoint. And when we did these calculations, we started out with 40 cubed, 60 cubed lattices, and we placed the critical endpoint in the wrong place until we finally went to lattices larger than 100 cubed. And only then we were able to see the true easing in 3D, this case, critical behavior. So there are examples where the approach to a critical point is not smooth, really. You have to overcome a critical size, and only then you are on the right track. So
yeah, so that also depends. You should also share what the transformation that you used was, because you know that this heavily depends on the choice of the renormalization group transformation that you did. So let's say
we just took the standard action and we just simulated with very efficient methods. So there was no explicit renormalization group transformation involved. We were just looking for the location of the critical endpoint.
Yes, so if there is no, I mean, if you don't rely on a renormalization group transformation, I would expect that the first point where you can start having an accurate estimate of criticality in the case of the Ising model should be L equals 1000. At least that's what I have with other methods and what I've seen in the literature. So
what I'm saying is you should, if you want to convince skeptics like myself, maybe you can work on that 3D Potts transition and show that your method can do it on a much smaller lattice. I would be very surprised, but
yeah, I mean, yes, I understand that this.
Yeah, I think I take this offline since I mean the discussion will be long on this point. So if you don't mind, we will take this offline. I'd like to pass to a question from the audience, from Luigi, and then Jan.
Hi, Dimitrios. This is a related question, and I apologize because I should read your papers much more carefully, which I will soon. My question is probably related to what Uwe Jens was trying to find out. When you do these inverse transformations, in a sense, there is a lot of freedom in the sense that you can, when you invert the renormalization group flow, you can actually add arbitrary irrelevant operators to your action. And how can you be sure that this specific inverse transformation keeps you, on the sort of same trajectory? How do you know that it's like having different improvements to your action? How do you know that it's always the same sort of improved action that you're simulating as you go to larger and larger lattices?
Yeah, so in this Monte Carlo renormalization group approach is slightly different than other methods. I didn't go into these details, but what we do is, so let me see if I can find something to make this clear. I shouldn't have. So what we do is we actually treat the renormalized system based on the probability distribution of the original. So that's something that we are free to do because this is an implication of the definition of a probability distribution. So you treat your rescaled system in a way as if it has the coupling constants of the original system. Now, the reason that this works is because you are then, in a way, that's what allows you to construct these explicit mappings that I showed you in the previous part of the talk, actually. Let me see. Yes, so that's how you are able to construct this mapping. So this is an approximation which goes back mostly towards the Kadanoff scaling picture. However, this approximation is good enough to give you what you want, at least in the system that we have studied. I don't know if that answers your question. I don't have an explicit answer of what would happen in a more complicated system, but for here, you are perfectly fine with what you do. Also, you can sort of feel safe because you can first verify that the standard renormalization group method works before you decide to invert it in a way. So that's also something that guarantees that what you do is safe, because you can first show that the standard case works, then you invert this standard successful transformation.
Okay, so thanks, Dimitrios. We will take this offline if needed, and I'd like to move to Jan.
Yeah, hi, Dimitrios. Thank you very much. I mean, it was a really nice talk, and I like the stuff. I follow essentially the questions of the two previous questioners. I mean, usually if you extrapolate with machine learning, you lose. If you go to larger samples, you lose within one order of magnitude, essentially contact to your original distribution. And this has been tested in loads of cases. So if you go to the, it's essentially the same question as Uwe Jens. So if you go to the larger lattices and you look at correlation functions, have you tested that you really get the moments of the distributions right?
So again, we are in the context of the Monte Carlo renormalization, the inverse Monte Carlo renormalization group, right?
The question applies to both, actually, of your both parts. But anyway, take the inverse renormalization group.
Okay, so yeah, in a way, you can verify that you have the correct result, but of course, in a shifted point in parameter space, which you can explicitly determine via the construction of these mappings that I have only done in the standard renormalization group. So here you can see where your system has been shifted to.
Okay, thank you, Dimitrios. Time for one urgent question. Yep.
Okay, I have a different question. So in the first part of the talk, you used these observables defined by the machine learning function. I mean, what do they cost typically to evaluate? And I mean, how does the cost of these things change as you change the volume or lattice spacing or systems, dimensionality of the system?
Yes, so considering the first part, of course, this becomes more computationally challenging the more you increase the lattice size, because it depends on a finite size scaling analysis. So, of course, these results are computationally expensive compared to what you will do if you were using conventional observables. At the same time, the idea is to apply this method in the case where you don't know what the order parameter is. However, the second part of the talk, where we use this observable to do the calculation with the renormalization group, is of course again not as computationally expensive, because you can get the result on much smaller lattice sizes. So there you don't really have the same problem as you do in the finite size scaling analysis. It's very easy to construct this neural network function on a small lattice size.
Okay, thank you very much. I think we need to move on. Let's thank Dimitrios again.
Thank you.